Hi, welcome to Hashtag Math. We will talk about vertical asymptotes of rational functions. They give us lots of information to obtain the final graph of these functions. Let's start. We first see how a vertical asymptote looks in a graph. 1 over x is not defined at 0. If you plug in 0, you get 0 in the denominator. That means we have a vertical asymptote at 0. Look, the behavior of the graph is it is approaching the asymptote, but it will never touch it. You never touch a vertical asymptote. The graph of 1 over x squared also has a vertical asymptote here at 0, and the graph is approaching in a different way, but your graph is always approaching your asymptote. Let's look at the next graph here. This graph has two vertical asymptotes, one at -3 here and one at 5 here. When you see the behavior of the graph is approaching the asymptote. It's always approaching the asymptotes. You see? Here, here, here. That is the behavior of the function. The function approaches the asymptote and never touches it. What does it mean that our graph is not defined at -3? If we look at the equation, we must have a factor of x plus 3 in the denominator so that -3 makes the denominator of that function 0. Make sense? If 5 is a vertical asymptote, means the function is not defined at 5, and that means that we have a factor of x minus 5 in the denominator of that equation. What's in the top? I don't know. Here, a heads up. Let's see what's happening at x equals -3. Your graph is approaching like that. The function approaches both sides of the asymptote towards the same place. Whereas at 5, from the right approaches positive infinity, from the left approaches negative infinity. So at -3, the graph approaches both sides of the asymptote towards positive infinity. At 5, it changes signs. One side approaches from the right to positive infinity, the other side from the left approaches negative infinity. Let's go back to our previous graphs. Okay, you can see here that 1 over x has the behavior of approaching one side to positive infinity and the other side to negative infinity. As my graph approaches the asymptote, it changes signs. That is associated to the power of x here. Because it's a power of 1, there is going to be a change in sign. If x is positive, 1 over x is positive. If x is negative, 1 over x is negative. And you see the change in signs. For 1 over x squared, we see that the behavior is different. The function approaches the asymptote towards positive infinity on both sides. Positive infinity and positive infinity, from the right and from the left. And that is associated to this number here, the power. You see, if x is positive, this is positive. If x is negative, still positive. So if you have an even power in the denominator, the behavior is either going up like that or down. But the graph shows the same behavior when it approaches the vertical asymptote. So if the exponent of the factor corresponding to the asymptote is even, the behavior is the same from both sides of the asymptote, going either to positive infinity or negative infinity. Whereas if the power of the corresponding factor is odd, then there's going to be a change in signs. And the behavior is one side is going to positive infinity, the other side is going to negative infinity. What does that tell us about the equation of the function we were looking at? Okay, so let's look at -3. There's no change in signs. On both sides, the function is approaching the asymptote towards positive infinity. That means that the power of the corresponding factor, -3, which is x plus 3, has an even exponent there. What happens at x equals 5? Okay, the function is approaching from the right to positive infinity, from the left to negative infinity. That means it's changing signs, and that means that the power of the corresponding factor, which is x minus 5, is odd. The actual equation of this graph, we're not ready to know it, I'm just telling you, is 15 times x minus 1 divided by x plus 3 squared times x minus 5. An even power when the function approaches in the same way both sides of the asymptote, and an odd power, because this is a 1 here, when the graph approaches positive infinity on one side and negative infinity on the other side. That's the heads up. Okay, let's look at the next example. Let's look for vertical asymptotes of this function. What's the domain of G? Domain of G is the set of all real numbers where x is different from -1, because -1 is the one that makes my denominator 0. What that means is the function is not defined at -1, and so we have a vertical asymptote here at -1. The vertical line x equals negative 1 is a vertical asymptote of the rational function g. And the behavior of the function towards that asymptote is going to be the same on both sides because it's even. So the behavior towards the asymptote is going to look either going both sides to positive infinity or both sides to negative infinity. How could we know if it's positive infinity or negative infinity? I guess the sign would tell us. Take a number close to negative 1. Maybe we can take just x equals 0. Plug in 0 into the equation. So if you put a 0 here, the sign of the top is going to be negative because it's negative 3. If you plug in a 0 here, the sign of the bottom is always going to be positive because it's being squared. That means that at 0, my graph, it's below the x-axis. That means the behavior is like this and hence like this. So this is not happening. Okay, let's go to the next example. Let's look first at the domain of G. The domain is closely related to vertical asymptotes. I'll explain later why I say closely and not equal. The domain of G is the set of all real numbers x such that x is not what? Negative 3 because it makes this piece 0. 1 we have to take out and negative 1 we have to take out. So we have 3 vertical asymptotes. 1 at negative 3 here, vertical asymptote right there. 1 at 1 and 1 at negative 1. The vertical asymptotes are x equals negative 3, meaning the line x equals negative 3, the line x equals 1, and the line x equals negative 1. Let's see now how the rational function approaches those 3 vertical asymptotes. Let's go one by one. Now, let's look at the behavior of the function as it approaches the asymptote x equals negative 3. The corresponding factor, x plus 3, you see, it has an even power. That means it is approaching the asymptote towards the same place, either positive infinity or it's approaching from both sides to negative infinity. How do we know if it's positive infinity or negative infinity? We plug in a point. Let's plug in the point x equals negative 4 into the equation. If you put negative 4 here, negative 4 plus 2 is negative. So this piece is negative. If you plug in negative 4 here, this piece is negative. If you plug in negative 4 here, doesn't matter. It's always positive because it's squared. If you plug in negative 4 here, this piece is negative, and if you plug in negative 4 here, this piece is negative again. We're multiplying the signs to get the sign of G at negative 4. We're only interested in the sign. So we'll multiply negative times negative, positive, times positive, positive, times negative, negative, times negative, positive. You see, 4 negative signs is positive. That means that the behavior is like that. Going to positive infinity. The graph is approaching positive infinity from both sides at the vertical asymptote x equals negative 3. Now let's analyze the behavior of the function near the asymptote x equals negative 1. You see, the corresponding factor is x plus 1. And the power here is 1. That means it changes signs. It either ends towards positive infinity from the left and then towards negative infinity from the right, or it ends towards positive infinity from the right and towards negative infinity from the left. How do we know that? Well, we plug in a point. We can plug in the 0. So if you plug in 0 everywhere, what are the signs? We only need the signs. So this is positive, this is negative, positive, negative, positive. So when we multiply all the signs, we get 2 negatives and the rest positive. So that's positive. So how's the behavior? 0 here is to the right. So we're approaching from the right. That means from the right is positive. So it's approaching positive infinity from the right. If it approaches positive infinity from the right, and we know that the exponent is odd, it will approach negative infinity from the left. It has to change signs because the power is odd. Now let's analyze the behavior as the graph approaches the asymptote x equals 1. The corresponding factor is here. It has a power of 1, so it has to change signs. So it approaches like this, or it approaches like this. Which one is the 1? The same 0 tells us that it is positive. So this is the behavior when we approach 1 from the left. Since that is so, and because the power is odd, then from the right, it has to approach negative infinity, the opposite sign. So that's the behavior. Let's look at the next example. I already factored because we need everything factored. Always remember this. The numerator gives us the x-intercepts, and the denominator gives us the vertical asymptote. Okay, so let's look at the domain of f, first of all. That is the set of all real numbers except what makes my denominator 0. All real numbers except 0, negative 2, and 3. We certainly have a vertical asymptote by looking at the graph. This is the graph of that function, by the way. We're going to analyze both things at the same time, the graph and the equation. We see clear that we have a vertical asymptote here at 0, and then a vertical asymptote here at 3. But what happened to -2? There's no vertical asymptote there. Okay, that is because the x plus 2 canceled out with the x plus 2 in the top. So even though the -2 is not in the domain, it is not a vertical asymptote either. So what's happening is not defined there, but, well, it's just a hole. At -2 is just not defined. Nothing else is happening there. There's no vertical asymptote. You see, the graph is not approaching any line. This is just a hole. Or it is also called a removable discontinuity. Let me write that. The function f of x has a removable discontinuity at x equals -2, because the corresponding factor there canceled out with the same factor on the top, producing that hole over there. We also say that the function has a hole at x equals -2. Okay, I hope this is clear. Let's look at the next example. What happens if I take the same function but multiply by x here? Well, now all this factor and all these factors cancel out. So the factor x, which corresponds to 0, produces another hole. So now we have a hole at -2 and a hole at 0. That's all. If there is a point where the function is not defined and cancels out with a factor from the numerator, then you don't have an asymptote. You have a removable discontinuity or a hole. Let's look at this example. You see your rational function, the first thing you do is factor it out. Then remember, again, the numerator gives x-intercepts and the denominator gives asymptotes, or the domain also. Okay, let's look at our equations and see what's happening. Okay, this factor canceled out with this factor. We know that at x equals -1, h of x has a hole, or a removable discontinuity. -2 makes 0 this factor, and it does not cancel out with anything in the numerator, so we know that at x equals -2, h of x has a vertical asymptote. You see how we're finding information towards our graph? Well, we can determine the behavior near that asymptote. We also have the x-intercepts. We know that 0 is an x-intercept and -4 is another x-intercept. Be careful, -1 is not an x-intercept. It's a place where the function is not defined. It's a hole. So we have only two intercepts, 0 here and -4 here. You see, more information, more and more information. We can also say the behavior of the function as we approach the asymptote. It's x equals -2. And look at the exponent of x plus 2, the corresponding factor. It is even, so it behaves both sides going to positive infinity or both sides approaching negative infinity. How do we know? Plug in a number. Let me erase a little bit this mess. What we don't really need is this piece because it cancels out. It's the same sign. It's not going to change the sign. So plug in a 1. The 1, when you plug it here for x, is positive. When you plug a 1 here for x, is positive. When you plug in a 1 here for x, it's also positive. That means that at 1, my graph is above the x-axis, is positive, meaning that the graph approaches the asymptote x equals -2 towards positive infinity. As you approach from the other side, you would have to go again to positive infinity because there's no change in signs. And that's the behavior near -2, and those are the intercepts. Next, we're going to do horizontal asymptotes to get one more piece of information because our goal is graph a complete rational function. Thank you.